What's going on, guys? We're back again with another video. We're just gonna jump into it. Everyone knows the deal. So let's just jump into it. Last time we introduced the idea of a critical point. I just want to remind you this is simply a point on the function f of x where the derivative is 0 or is undefined. So that guy came. The reason why these points were considered critical to us is because we had something called Vermont's theorem last time that basically said that if you have a function attaining a maximum or a minimum at some point and the derivative exists, then the derivative must be 0. We showed examples that the converse was not true, which means it's possible for the derivative 0 but you don't have a max or a min. It's also possible for the derivative to not exist but you have a max or a min. But either way, that theorem really kind of hinted to us that one of the places we cared about, at least when it came to Extrema, which remember is another name for maximum or minimum, is points where the derivative is 0 or undefined. So Vermont's theorem kind of hints to us that this point might be important to check out, even though it's not guaranteed to be a maximum or a minimum. Wherever the derivative is 0 has a chance of being a maximum or a minimum. That's why we actually want to check it out. We also know from examples like the absolute value of x function, which has a sharp corner at the bottom, so the derivative isn't there, but we know it has a minimum there. That also gave us the idea of checking when the derivative is not defined, because you might have a max or a min that ends up at a sharp corner or something like that, and we'd want to identify those points. So we considered both these points as critical points. When it comes to finding Extrema, the critical points are going to be an important part of the mix. So that was our definition there. You need to know that definition by heart. We call something a critical point if the derivative is 0 or undefined there. We also saw the EVT, the extreme value theorem, which basically says if you have a continuous function on a closed interval, then it is guaranteed to attain its absolute max and min on that interval. And in fact, me actually reading that reminds me of a question that came from our viewers. This thing logged out here. Yeah, so it seems that for the most part, students understood the last lecture, but I did get a question on the extreme value theorem. Yeah, so someone asked, so according to the, hold on, let me check something. So I think this was the only question that I got from this class, if I'm not mistaken. Yeah. Okay, so the question is as follows. According to the extreme value theorem, we're supposed to always get a global extrema for continuous functions on an interval. Slight mistake there, on a closed interval. So no, it won't work on any interval. It has to be a closed interval. Okay? So if you have a function that's continuous on a closed interval, meaning it has endpoints, it is of finite length, then yes, we're guaranteed to have absolute maximums and minimums. If we're not on a closed interval, it's not guaranteed. We might have it, but we also might not have it. So for example, absolute value of x, like I was mentioning, that has an absolute minimum as long as you're looking at any interval that contains the origin, because it has a minimum at the origin. But I wouldn't be guaranteed to be able to find it anywhere if it's an open interval, right? So if I were to look at the absolute value of x on the open interval from 1 to infinity, not including 1, then that guy has no absolute max. It also has no absolute min. So that's one thing that you want to be careful of. It has to be a closed interval. So the extreme value theorem applies to continuous functions on closed intervals. So the interval can't be infinite. It also has to be finite length. So does that mean that on an interval, a continuous horizontal straight line would have all points being the absolute max and absolute min? The answer is yes. And that's a very good thing that you saw that. So if you have a horizontal line, right, so you are on subinterval AB, and you have, it's continuous on that interval, so you have a horizontal line. Yes, it turns out that every single point is an absolute max and at the same time an absolute min. So it definitely has an absolute max and an absolute min. In fact, it has an infinite number of each. So for a straight line, it will attain absolute max anywhere. And namely, you would also notice that every point along a horizontal line is a critical point, because at every point you have the slope being 0. It's also true for just any straight line that's not horizontal. So if I have a line that's not horizontal, then it will also attain its absolute max and min on this interval. Namely, it will hit the absolute max at the right endpoint, it will hit the absolute min at the left endpoint. If it was slanted this way, it'll hit the absolute max over here and the absolute min over there. But yeah, this does apply to straight lines. It does mean that you will it will hold for straight lines. It will either hold at the endpoints, or if it's horizontal, it will actually hold for all points. So you can have an infinite number of these guys here. So when we say it attains an absolute max and an absolute min, that's a math way of saying at least one. So yeah, that was a good question, very insightful. So yeah, if you have a horizontal line on a closed interval, it does attain absolute maximums and minimums on that interval. In fact, all its points are absolute maximums and minimums. So yeah, I did not get any other question on this, so I think the last lecture was mostly well understood. A lot of it was definitions anyway, so it's just me giving you some information, telling you about theorems. So it's just stuff to know as opposed to understand most of last lecture. So I guess that's not too surprising. Yeah, so we have that from the extreme value theorem. We spoke about that last time. Continuous functions on closed intervals are guaranteed to attain absolute maximums. Okay, let's move on. Now what I want to talk about, since last time we started talking about absolute extrema and local extrema, I want to figure out how can we actually find these guys. It's going to be very important to locate these kinds of points, extreme points for various situations. Now, when it comes to finding the local extrema, we actually know how to do this already. This was way back in lecture 10, so if you look in this playlist, scroll up to lecture 10. In lecture 10, we spoke about the first and second derivative test. The second derivative test, kind of superfluous, it's not going to be necessary. It's also harder to get this guy to work than the first derivative test is, because the first derivative test will work in the case where your derivative is not defined, but the second derivative test actually needs your derivative to be continuous for it to even apply. So second derivative test, I don't really like using it in practice. It's cool, I guess, but in a calculus class 1, you would tend to have to do the first derivative test anyway. So once you do the first derivative test, it makes the second derivative test kind of unnecessary. No one's going to jump straight to the second derivative test. It's harder to get it to actually apply. So the first derivative test, that's the one where you test where the derivative is positive and negative, and you know that if it's positive on the left and negative on the right, then that means it does this, which means you'll hit a maximum as long as the function is continuous, and so on and so forth. So you can review lecture 10 for that. That's how we find the local ones. For the absolute ones, that's a whole other story, because as you'll notice here in the straight line example, so let me even use this example, it's not that you will always, the first derivative test wouldn't be able to identify a maximum or a minimum on this function. The first derivative test is nice if your function like went up and then back down, and you can identify that because you'll see, oh, positive slope, negative slope. But what if your slope was 0 the whole time? How is it going to identify a max or a min? Well, there is no local max or min technically. Well, technically there is actually. But in a more general sense, for absolute max or min, it doesn't have to be something that looks like a hill or a valley. If I go back to the example where we had a slanted line, and that was the whole function. Notice that the first derivative test wouldn't actually identify that as a maximum because there's no decreasing part to kind of match up with that increasing, decreasing dynamic. So you always see this thing where you're increasing from the left, it doesn't show the decreasing portion, and so it's not really going to pick it up as a max or a min. So the absolute max or mins, it can happen at endpoints which might not look like a hill, or the minimum might not look like a valley, so we need a whole other method for this one. The method is called the closed interval method. So I'm going to introduce that method to you, and we're going to do an example using it. So the closed interval method is a three-step method. Okay, so suppose f of x is continuous on AB, right? So this method will only apply to a continuous function on a closed interval. And I'll always, whenever I ask you about finding absolute max and mins, I'll actually always give you this situation. I'll always say, here's a function, it's going to be continuous, and I'll give you an interval. It'll be a closed interval, and I'll ask you, find the absolute max and min on this interval. Okay? So we know that it exists by the extreme value theorem. So how we can find, here's how we find the absolute extrema. Which we know exists by the intermediate value theorem. Ever so often, I'd ask a question like this, and a student would respond with something like, oh, this function has no absolute. Like, it has to have one. It has to. It's guaranteed to have one. The extreme value theorem tells you that. Every now and then I see that, and whenever a student writes down an answer like that, they're trying to sound all sophisticated. Therefore, you know, they write down like 10 steps. Therefore, there's no absolute max. Like, dude, you're contradicting the extreme value theorem. There's definitely an absolute maximum. Okay, so we're looking at a closed interval, and it's a continuous function. Here's how you can find the absolute extrema. One, you're going to find all critical points in AB and evaluate F there. Meaning, you're going to find all the x values where your derivative is 0 or undefined. Then you're going to plug those into the original function, and you're going to find the corresponding y values. That's what it means to evaluate f. 2. What this guy is going to do, it's going to examine all the critical points, the kind of guys that would be picked up by the first or second derivative test. You're going to figure out their y values here. Now, the example that I gave you earlier with the straight line, notice that the absolute max or min might occur at the endpoints, and your first derivative test cannot identify those guys. So the next step you're going to do is to actually check the endpoints. Evaluate f at the endpoints. i.e., find f of A and f of B. So you're going to find all the critical points, the kind of guys who would give you maxes or mins with first derivative tests, perhaps. Then you're going to find what f is doing at the endpoints. Now the next thing you're going to do is you're going to compare the above y values. So you will, if you find critical points, you'll get some y values here, but you'll definitely have at least 2 y values, namely the guys in step 2. So you'll have 2 y values or perhaps more based on step 1. You're going to compare all the y values, and that's pretty much the last step. The largest y value, well, that's your absolute max. And the smallest y value is your absolute min. And there's a special way that we like to write this down. I'll let you guys know when we do an example. But that's it. The closed interval method is a 3-stepped method. It applies to continuous functions on closed intervals. So I'll give you a continuous function, I'll give you a closed interval, and I'll say find the absolute extrema on this interval. And you're going to go through these 3 steps, always these 3 steps. It's called the closed interval method to actually find all the absolute extrema. So I will give you some time to copy this down. Let me get my big head out of the way. Pause the video. I'll give you 3 seconds to pause and copy it down. 3, 2, 1. And okay, hopefully you pause and copy that down because we're going to jump right into an example and you're going to need to know these steps. You're going to need to know these steps for the example. So here's an example. Suppose f of x equals, I think I give x to the 4th minus 2x squared. I want to say, what was the example I picked here? Minus 4x squared. Find the absolute extrema of f on the interval minus 1 to 3. So, a couple things you can notice here. This function is a polynomial function. We know that polynomials are continuous everywhere, so for sure it's continuous on that closed interval. So we have a continuous function on a closed interval, and I want you to find the absolute maximum and minimum on this interval. So copy that down. Here's what I'd like you guys to do. As usual, pause the video, actually try to do the problem, see what you can do. So I'll give you 3 seconds to pause it, then you can start again and see if you got the answer. So 3, 2, 1, pause the video. Okay. Hopefully you actually tried it. So, here's how you go about a problem. And if I put a problem like this on a test, it's pretty much almost going to look exactly like this. I might lead with this sentence. Find the absolute extrema of f of x equals this on this interval. Or here's a function. Find the absolute extrema on this interval or whatever. Another way I can write this interval down is I can say minus 1 less than or equal to x less than or equal to 3. So I might write the interval as an inequality as opposed to in interval notation. But other than that, the problem is going to look somewhat like this. But the goal here is to find what is the largest y value that this function attains on that entire interval. I don't care if it looks like a hill, right? And what is the smallest y value that it attains on that interval? I don't care if it looks like a valley. It could even end up at the endpoints where there are no hills and valleys. And yeah, actually find them. So we would jump into the closed interval method, and that would go like so. So first step 1, we're going to find the critical points. So what we're going to do for critical points is find f prime of x. What's f prime of x? That's right, it's 4x cubed minus 8x. Now, for critical points, set f prime equals 0 or undefined. Now, f prime is itself a polynomial. It's never actually undefined. So we don't even have to worry about that part. So let's just worry about setting f prime equals 0. So this means that my 4x cubed minus 8x equals 0. What's the solution? If you didn't get up to this far, at this point, pause the video. At the very least, you should know how to actually solve that equation. That thing totally just freaked me out just now. The screen just came down a little and went back up a little, and I didn't touch anything. This actually happened last night around this time, so I think there's, I don't know, some sort of program set, and it's kind of freaky. Did you get the answers? Okay, so we know how to solve polynomial equations. Hopefully the goal is to factor the left side and set each factor equal to 0. Common factor here is 4x. That would leave us with x squared minus 2 equals 0. So this would mean that your x equals 0, or your x is equal to positive radical 2, or your x is equal to negative radical 2. So just a little bit of pre-calc there, or algebra, I don't know when you would have learned that. So remember, you're going to find the critical points and you're going to evaluate them. But there's something very important here. So in the closed interval method, well, maybe, can you tell me what is something that you'd want to be considered here? We have these 3 points. So for me to be very suggestive, I might ask the question, do we actually want to find the y values for each of them? Are they all going to be applicable? And the answer is no. And if you read the closed interval method closely, what you want to do is you want to find all critical points on the interval. And what you'll realize is that radical 2 is actually around 1.4, so that is clearly inside here, but the negative radical 2 is not inside there, because negative radical 2 is actually negative 1.4. It's actually outside of this interval. So this one you would reject outside the interval. But in the meantime, what I'm going to do is I'm going to evaluate f at these 2 points. So I'm going to have f of 0, which I'm going to plug into the original, 0. Then I'm going to have f of radical 2, which is going to be, well, radical 2 to the 4th minus 4 times radical 2 squared. Radical 2 squared is 2. You square that again, you get 4. Here, so you get 4 minus 8, that's minus 4. So those are the 2 y values. So this is step 1 in the closed interval method. I'm going to erase this side, so pause the video, copy that down. Alright, let me jump back in here. Now we'll move on to step 2. Let me leave my function up here so I remember what that is. In step 2, you're going to test endpoints. So the endpoints were minus 1 and 3. So I'm going to find f of minus 1. Well, that's just going to be minus 3. Right, because that's going to give me plus 1 minus 4. Then I'm going to find f of 3. That's going to be 3 to the 4th minus 4 times 3 squared. And that's 9 times 3 squared minus 4 times 3 squared, which is 9 apples minus 4 apples, 5 times 3 squared. So it's 5 times 9, it's 45. Okay. So we first found the critical points were at 0 and radical 2, the ones that are applicable. The minus radical 2 doesn't apply. We found that f of 0 was 0. We found that f of radical 2 was minus 4. Now we test the endpoints, f of minus 1 and f of 3. These were minus 3 and 45 respectively. Now we go on to step 3. Compare. So all you're going to do is you're going to go through here. You're going to find the absolute max and absolute min by just picking out the biggest and smallest values. Now from all these values, 0, minus 4, minus 3, and 45, clearly the largest one is 45. So you write it in this way. You say f of 3 equals 45 is the absolute min, max. And we like to actually write it out this way. You identify the y value as well as the x value that achieves that y value. You normally want to write out the answer in this way. And next you just pick out the smallest guy. So out of 0, minus 4, minus 3, and 45, who's the smallest? Well, the minus 4 is the smallest. So this is f of radical 2 is minus 4 is your absolute min. And that is your answer. So that's the closed interval method. You have a continuous function on a closed interval. First find the critical points. Make sure that you're finding the critical points that are in the interval. You evaluate all the y values there. Then you evaluate the function at the endpoints. Then you compare all of them. Pick out the biggest guy and the smallest guy. That's your absolute max and your absolute min. Notice that one of your absolute extrema occurs at the end point. Now we are. The next topic we're going to go into is curve sketching, so I don't know if I want to lead with that and. Let me just do it. Okay, so here, notice that your y was x to the 4th minus 4x squared. You could actually factor out an x squared here. You get x squared minus 4. You can factor that further. You can get x minus 2 times x plus 2. And what you would notice there is your x-intercepts. This is not a part of the answer. This is something else. The problem is finished here. Your x-intercepts here will therefore be 0, 2, and minus 2. So if you wanted to draw this graph, it will pass through 2, 0, and minus 2. And by testing values, like plugging in x equals minus 3, you'll see you get a positive answer. X equals like minus 1, you'll get a negative answer. X equals 1, you get a negative answer. X equals 3, you get a positive answer. You'll figure out that the graph looks like this. It's a W. And what we're doing is we're looking at the part that goes from minus 1 this dip actually happens at minus radical 2. This actually happens at positive radical 2. So minus 1 means we're starting from like here. So we'd ignore this part. And then it goes up to 3, which is going to stop it somewhere here. So if you want to look at what this looks like as a picture, this is our graph. Notice that it starts here, it dips down to its minimum point on this interval at radical 2, then it increases towards its maximum point. It hits an absolute minimum here, it's an absolute maximum there. Now, that kind of naive curve sketching, you would have done it in a pre-calc class, but we're actually going to do sketching in a lot more detail in this class. So if you forgot how to sketch, don't worry about it too much. We will get back to it. Yeah, that's your absolute max and min on the closed interval, by the closed interval method. So here was your absolute min, and here is your absolute max. And we identified that without knowing how to draw the graph. Like, we knew that that's what would have happened, which is pretty cool. We actually can figure out where these points happen without even knowing what the picture looks like. Now, the next topic that I want to do, we're moving on into the next section, which I forgot what number that section is in your textbook, but it's pretty much a section on curve sketching. Before jumping into curve sketching, I want to talk about, gonna get chalk in my hair. Let's talk about something called asymptotes. That's going to be important for us to understand for curve sketching. And at this point, how much time is left? I don't know. I'm definitely not going to complete curve sketching today. I might start it, I don't know. Asymptotes. So, fuzzy definition here. You have the graph of some function. An asymptote is a curve, a graph, approaches as the x or y coordinate becomes infinite. We will care about two types specifically. I don't know why I underlined that. We will care about one so-called horizontal asymptotes, and two vertical asymptotes. Okay, so there are many kinds of asymptotes. You can have slant asymptotes, oblique asymptotes, you can have asymptotes that are just, they can be any curve, right? So it's just like you have a graph, and you might have some curve that's not really on the graph, but you realize that your graph gets close to that curve as, like, for example, your x-coordinate is going off to infinity. As you move on to the right, the closer the graph is going to get to this curve, right? There are two special types of asymptotes that we're going to want to know about for curve sketching. That is the horizontal and the vertical ones. So here's an example. If you look at y equals 1 over x, we know the graph of that. Looks like this. What I want you to realize is that this has both horizontal and vertical asymptotes. Notice that there's a vertical asymptote at x equals 0. As the y-coordinate is going off to infinity, the graph is approaching the curve x equals 0. So that's a vertical asymptote. As your x-coordinate is going off to infinity, notice that your graph is approaching y equals 0. So y equals 0 is a horizontal asymptote. Right? So as your x is going off to infinity, the graph keeps getting closer and closer and closer to this curve, namely the curve y equals 0. As your x is going off to negative infinity, your graph keeps getting closer and closer and closer to that curve. That means the line, since this line is horizontal, it's called a horizontal asymptote. It's just the equation of a horizontal line. A vertical asymptote has the equation of a vertical line, namely it's x equals a constant. In this situation, it's x equals 0. So, those are what asymptotes are. Now I want us to know how to find them or identify them. Now for some graphs you'll know right off the top of your head what they are, like with y equals 1 over x, because it's a very familiar graph to you. But what if I ask you about something that's not so familiar? How are you going to find these guys? So let's talk about to find horizontal asymptotes.
Let's call it HA.
All right, so we're going to take it way back. We're going to go back to limits actually. And technically, to find vertical asymptotes, you also need limits, but there are ways around it so that you probably won't have to think of limits when doing them. But for horizontal asymptotes, you're always actually going to be thinking about limits. Given f of x, what you do is compute two limits. Compute the limit as x approaches infinity of f of x, and the limit as x approaches negative infinity of f of x. Now, if one let's say if any any of these give you a constant value. So you take the limit as x approaches infinity and you get 5 as the answer, or you get 1 as the answer, or you get minus 17 as the answer. If any of these approaches a constant value, say call it k, then y equals k is a horizontal asymptote. That's how you find it. You just take infinite limits. Take limits at infinity. So as your x-coordinate is going off to infinity, you want to know, is your graph approaching any horizontal line? If you get a constant from either of these. Now in general, these two guys could actually give you a different answer in general. But for the problems that I'll be asking you in this class, they'll pretty much always coincide. So for rational functions at least, when you're going to positive or negative infinity, they'll always coincide. So for example, if I have a function that is the ratio of two polynomials, we know as a shortcut to find the limit as x approaches infinity plus or minus, it always goes to the ratio of the leading coefficients. So in that situation, both the limit as x is going to infinity, I can't even see if this pointer is the right place in the camera. Both the limit as x is going to infinity and the limit as x is going to minus infinity will actually return the same value, namely the ratio of leading coefficients. So for rational functions, you'll always actually get the same answer either way. But in general, you really should test both of them because it's, in theory, they could give you different answers, even though in practice, in this class, you're always kind of going to get the same answers from both of them. That being said, if either of them give you a constant, y equals that constant is the horizontal asymptote. If they give you different constants, then you have two horizontal asymptotes. So this one, you take this one and it gives you 5. That means the line y equals 5 is a horizontal asymptote. Then you take this one and you got 7. Then that means the line y equals 7 is also a horizontal asymptote. As you're going off to the right, you would approach y equals 5. As you're going off to the left, you would approach y equals 7. Okay? So as long as one of these guys give you a constant, that is called a horizontal asymptote. So example. So I say f of x equals, say, I don't know, 1 minus 3x squared over 2x squared plus 4. If I take the limit as x approaches infinity of f of x, I would actually get minus 3 over 2. And the limit as x approaches negative infinity of f of x, this is also minus 3 over 2 because of ratio of leading coefficients. This means y equals minus 3 over 2 is an HA. Okay? So that's the way to find horizontal asymptotes. You just simply find the limits at infinity. Now, we are going to do a lot more examples of this when we get to curve sketching, the next topic. But right now, I just want to kind of introduce this first, because finding asymptotes is going to be one step in the multi-step process of doing a curve sketch. So I wanted to actually just isolate this, deal with them separately, and then we're actually going to use this in conjunction with a lot of other things. So that's how you'd find horizontal asymptotes. Let's talk about finding vertical asymptotes.
which I'll abbreviate to VA.
Let's find the vertical ones. So for these, they're a little bit trickier in general. But for the kinds of functions I'll ask you about, there's actually a nice little shortcut for how to actually find them. So, here's the definition. X equals A is a vertical asymptote if the limit as x approaches A from the right of f of x is a vertical asymptote of f of x. If the limit as you approach A from the right is infinite, either plus or minus, or the limit as you approach A from the left of f of x is infinite, plus or minus. Now, in general, depending on what your function looks like, figuring out what values you have to get close to in order to shoot up to infinity or down to negative infinity might be a little bit confusing, but if f of x is rational, like a ratio of polynomials, this, what I mentioned up here, happens precisely when a factor, meaning you should be able to factor the denominator, a factor in the denominator goes to 0 and no factor in the numerator can cancel this. So, for example, so pretty much, so one thing you want to do is check where the denominator hits 0. So all the questions that I'm going to ask you, where I'm going to ask you to find a vertical asymptote, is usually going to be a rational function where you can find the denominator 0. All the other nice situations where I can actually ask you to find these things would be with trig functions, but in this class we don't deal with trig functions. So, so check where denominator is 0. But just make sure that there's nothing in the numerator that cancels that. So for example, if I have f of x equals 1 over x minus 2, then x equals 2 is a vertical asymptote. Right? I don't need to check what limit's going to go to infinity. All I just need to look at is where's the denominator hitting 0. Now you will know from this graph that that is true. If I approach 2 from the right, I get positive infinity. If I approach 2 from the left, I would get negative infinity. 2 is actually, it fits the definition of a vertical asymptote. Notice that the numerator is, it does not allow me to cancel that x minus 2. We have seen other examples. So we saw something like x squared minus 4 over x minus 2. Now in that case, the denominator is 0 at 2, but x equals 2 is not a vertical asymptote in this case. Notice what would happen here. This is just x plus 2 times x minus 2 over x minus 2. So the 0 in the denominator can be cancelled. So this gives you a whole. You get a whole at x equals 2. Right, so we had that graph where we've seen this particular example before. There's just a hole here. So whereas this one has an asymptote, that happens because you couldn't actually cancel the 0 in the denominator. Whereas in this one, you can simplify it so that the 0 cancels. That's technically not what happens, but you get the idea. Right? In practice, that's how you kind of think of it. If I can cancel the 0 in the denominator, there's no vertical asymptote. If I can't, it will hit a vertical asymptote at wherever the denominator hits 0. And that's how you find vertical asymptotes. So I see something like this, I would set the denominator equal to 0. So another example is if I'm looking at this function, f of x equals 1 over x squared minus 4 has 2 vertical asymptotes. Namely, x equals 2 is 1 and x equals minus 2 is 1. These are both VAs. So when you're drawing the graph of this function, there are going to be a vertical line at 2 and a vertical line at minus 2 that the function is going to approach either infinity or negative infinity as you approach these guys. Which one it will actually approach? Well, when we get into curve sketching, we will actually look at that. So, how to figure out the graph and how it's going to behave with these asymptotes. One thing you can also notice, if I were to take the limit as x approaches infinity of this, also, the limit as x approaches plus or minus infinity of this guy, you actually get 0. So 0 is actually going to be a horizontal asymptote. Now, there are many other things that are going to go into, say, drawing the graph of this guy, which we will get into next time. It's not enough time for me to get into it now. But that being said, I should mention that for curve sketching, we're going to be using another handout. I will post a link to this handout in the video description, I suppose, so you can download it. It is double-sided. So on the first page, I show you the steps that you would want to go through in order to actually sketch a curve. There are steps in here that involve calculus, some do not. Notice that step 3 is to find the asymptotes. That's just one step in like a 6-step process. So you are going to want to know how to do each individual step here. So I give you the steps to actually do a curve sketching, and I told you about some rookie mistakes right there, things you're going to want to look out for. And then I give you examples on the next page. Now, I'll probably do a couple of examples from up here just for you to get the idea, but chances are if I test you on something, it's going to be an example like what's down at the bottom. So I told you that calculus is going to be involved usually. So sometimes I'll actually just give you the derivatives. So I'll take that part of the calculus out for you because in general on a test, I would have tested your ability to take derivatives elsewhere. So I'm not going to test your ability to do derivatives on this thing. So yeah, I'll post a link to the PDF for this. Print it out or just download it, have it handy, because in the next lecture, it's all going to be about this handout. We're going to go through this handout. We're going to sketch a bunch of curves. That's all that's going to be in the next lecture. So have that handout ready, and we will get into it. So for today, we learned how to find absolute maximums and minimums. You should remember what those are. I covered what they are in the last lecture. So today we looked at finding absolute maximums and minimums. You actually need to know how to find local maximums and minimums, but I actually covered that in lecture 10. The other thing you want to pay attention to is how to find asymptotes. We are going to put a lot of things together. So we are going to do curve sketching. It's going to put a lot of things we've done in terms of asymptotes, in terms of calculus, in terms of first derivative tests, in terms of a lot of things. We're actually going to draw a lot of things by hand that you probably wouldn't have known how to draw by hand before this point. So that's what we're going to do next time. We're going to do a bunch of examples, just sketching curves. And we'll just do that next time. I was going to say something, but I don't want to go off on a tangent at this point. Have a good night, and hopefully I'll see you in the next one. As I said, this week I'll be posting mock quizzes just to give you some practice, and I will keep you abreast of what we will be doing for testing. So I will see you then. Be safe and keep studying. All right, ciao.